So in the easy example I've shown you there, you can get a nice, easy, tidy answer because you can get bases to be the same. What about if you were given something like this? Something really straightforward like 2 to the power of x is equal to 5. So follow the same steps as we did in the easy example. We first change 5 into 2 to the power of, come on, to the power of what? Yeah. There's only one good answer at this stage. Perfect. Yeah. There is no easy 2 to the power of that gets us 5. It's, I don't know, it's going to be more than 2 squared and less than 2 cubed, so it's 2 point something, but we don't know. But luckily, we don't have to do guess and check. So in grade 10 maths, or maybe maths extended even, you would probably just say, well, 2 to the power of 2.1 equals what? 2 to the power of 2.2 equals what? Until you get the right answer. However, when we know logarithms, then we can rearrange this as whichever way we want to. So, for example, I'm not even going, I could turn this into a log base 2. Okay, I could just simply say by the rules of how a logarithm is created, I know that x is going to be log base 2.5, and then use your graphics display calculator to work out what log base 2.5 is. Or I could take the log, note the log, and not log base 2 or anything, the log of both sides, it being handy because your scientific calculator will deal with that. And then just remember that there's that log law which says if I've got a power, then the power gets dropped down. So that's x log 2 equals log 5. And now I can say x is equal to log 5 over log 2. PS, change of base. It's the same thing. All I've done is I've changed base there. Absolutely not. So that would be the only exact answer we can say. If I said, what is the exact answer? What does x exactly equal in order to get 2 to the power of x equal to 5? The answer is log 5 over log 2. Not if it said do it to 3 significant figures, then you would go on your calculator. I'm doing it on my calculator to the side right now. I would go log 5 divided by log 2, and I would get 2.321928000949. So 2.32 to 3 significant figures. Oops. And does that reconcile with what I thought it might be? Sure does. I basically said that, did I not? Did I not say that it's going to be bigger than 2 squared and it's going to be smaller than 2 cubed, so 2.1, 2.2 or something? So that's all right, isn't it? All righty. So I've got this side view of my calculator on my iPad, and of course I can't dismiss it now because it's annoying. Okay, so that's basically that kind of thing. No, you do swipe for me. I just can't get it to work. Okay, so next example then. What I'm going to do now is I'm just going to go through a few different examples from the book, give you a quick opportunity to practice them, and then give you another example and move forward, okay? So whilst I'm getting everything sorted, if you could grab your textbooks open, please, and turn to page 128. I'm going to do an example from exercise 4P and then keep working my way through them and then give you a chance to practice a bit at a time. Just to give you a feel for what we're going to cover today, we're going to cover exercise 4P, 4Q, and 4R. So there's quite a lot to cover today. That's 3 different exercises. And what the heck, let's throw 4S into the mix as well. So PQRS. So you need to work fast. Page 128 is where we're going to start. No, actually, you know what? It's the opposite. I've just had some Nurofen. I'm really sick, and I'm worried that I'm not going to be here tomorrow. So I'm trying to make sure that you've covered everything. I did it. There are again, there are so many examples I could go through, but really hard to find something which is absolutely going to give it to us. So example 1 is from 4p, and it's question 1b, like so. So e to the power of x on 5 is equal to 0.11. So I've got e to the power of, so I'm going to use the opposite of e to the power of, and I'm going to use ln. When I take the natural logarithm of both sides, that will cancel out the e. Thank you. I've got no idea where I got the b from. Okay, let's cut the chatter so you can focus on the example, and then you'll have a little while to figure it out, Jeremy. Yeah. Yep. Jeremy. So I've taken the natural logarithm of both sides, knowing that that's a calculator operation. So I can now grab x over 5, and I can basically put it outside of, oops, like so. Didn't actually technically have to do this step because ln of e to the power of something actually cancels it out, each other out. So I technically did not have to do this, but I just naturally did it, to be honest. And then ln e is 1, right? Lols. What's wrong? Zoe? Oh, okay, the terrible pun. Yeah. No, I get the word. No, it was Richard's terrible pun. Unintentional. You're the one who brought its awfulness to the day. Yes, Ansel. Thank you, Ansel. I'm going through an example, and I was hoping you were following. That's what I was really hoping for. That's okay. So are we right so far? Yep. The last step, oh no, it's back again. The last step is to take the natural logarithm of 0.11 and multiply it by 5. And I get, oh gosh, 0. I think this is right. My calculator's gone weird on me. 0.0, oh, sorry, negative 0.0. Just check at the back of the book though, because I'm just worried my calculator's being a bit, not weird, but shortened in the way it's saying it. So 0.00739 to 3 significant figures. I think it's 0.0. Only because I'm not sure about what my calculator is telling me. What is it? 4p. Just looking at the back of the book to confirm what my calculator, well, that I can actually read my calculator. And can I read my calculator? The answer is, can I just do 1H? No, I cannot read my calculator. Try that again. Just hold please. I can read my calculator okay. I just can't put stuff into my calculator okay. So the answer is, yeah, negative 11.0. Sorry about that. I think in my calculator, Renus, I think I forgot to multiply by 5. And I have to put the O in, right, because I'm doing it to 3 significant figures. So I do need to have that 0. So that's a rounded 9 effectively. Okay, time for you to do some work. The best part of the recording, but anyway. Okay, so we have 2 to the power of x plus 2 equals 5 to the power of x minus 3. So we need to get at those powers, and so we apply an inverse operation in order to do that. So I'm just going to use log base 10 because I can. Okay, here's the trick though. When I take those powers down, because it's a compound term, it's made up of more than one thing, I need to put x plus 2 in brackets because I'm multiplying the whole thing by log of 2. X minus 3 is the power, and so when I bring it down, I need to bring down the whole of x minus 3 here. X plus 2 is the power, so when I bring it down, I need to make it the whole of x plus 2 here. We know that the law, which I'm going to write and then scribble out, is log a to the n equals n log a. We know that. That means n multiplied by log a. That's what it means. I have to multiply the whole of the power by log 2, which is why I've got brackets around it to show that x plus 2 is 1 whole power. Does that make sense, Jeremy? Didn't you say, can you please explain? Okay, so we've now got x log 2 plus 2 log 2 is equal to x log 5 minus 3 log 5. All of these are horrible numbers. I'm glad to see there's some light bulbs going off there. No, I'm not. I'm just practiced. I am definitely not a genius. No, I'm a bit over it, to be honest. You know what? How much of a genius I am, Jeremy? I can't even get this darn calculator off to the side of my iPad. I can't even get it to go off the screen. That's how depressing it is. Is it because there's that? No. Swipe downwards? Nope. You're supposed to slide off it. Yeah. It's supposed to go. You meant to. That's how you're supposed to do it. No. But there's a tab down there. You can swipe it. That's to swipe between apps. Oh. Oh. Could actually be the app. There was a little circle thing up there that they've got on the kids' ones. No, that's that one there. Oh yeah. That's how I can use a mouse with my iPad. Awesome. How long have you been a teacher? Too long. For the video, Ambrosia just asked me how long have I been a teacher. Okay, I'm going to finish this off. Treat log 2 and log 5 as just numbers, right? So I'm not going to evaluate them until the very end because I don't want approximation errors. But as usual, when I have a variable that I need to work out, I need to isolate it onto one side of the equation and then work it out from there. So I am going to, let me see now. I'm going to subtract x log 5 from both sides. And that will get me x log 2 minus x log 5 is equal to, and I'm going to subtract 2 log 2 from both sides. Okay, so I'm getting rid of the expressions, or sorry, the terms that don't have any x's in them. So I've effectively moved them over to the other side, but what I've really done is I've eliminated from that side and then balanced it on the right. And then I've moved the x's over to that side, and the way I do that is by eliminating it on that side and then doing the same operation on the other one. I haven't finished that line yet. Yep, that's why it's up here. Yeah, that's why it's up here. I just haven't finished yet because I can't get to the screen because of that silly thing that I told you about before. Oh, this is driving me crazy. Okay, so that's minus, so I'm left with minus 3 log 5 minus 2 log 2. Okay, now I've got a common factor of x on the left-hand side, so that's x outside of log 2 minus log 5, which equals minus 3 log 5 minus 2 log 2, just whatever it says. I'm not even worrying about trying to simplify it or anything at this stage. Yeah. But the thing is, though, is that the mess is created by you step by step and then fixed by you step by step. The problem is that if I start with this, and then if I said, well, from here, we go to here, of course it looks really, really messy and horrible. But that's not what we do, right? We unpack it one step at a time until we get there, and then it gets simpler and simpler. Yes, it's gone. So x is equal to negative 3 log 5 minus 2 log 2 all over log 2 minus log 5. Oh, this is an easy one. It's an easy one. What makes this difficult, Art? Okay, let's break this down, right? If you think this is difficult, let's pinpoint why you would find it difficult. In terms of new concepts, this unit concept that I've asked you to work on for this one. In the first line, you had to remember to take the log of both sides. That's something that you've done. In fact, you said that question 1 was way too easy, when in question 1, that's exactly all you're doing. In the second line, so this line here, I asked you to take a power and bring it outside the log like we've done a number of times. From that point onwards, the rest of it is grade 8 algebra with funny looking numbers. I'm serious. It's going to be on the thing, so that's fine. So I can play that when I'm doing revision. It's grade 8 algebra. No, I'm not. Listen, this is important. I'm not trying to belittle you and say, well, if you can't get this, you've just failed grade 8 algebra. My point is, you look at it and you go and you say things like, oh, this is really complex and you've made it really messy and untidy and I don't get it. But all you're doing is you're allowing your own brain to get in the way of what you have done since grade 8. I'm not trying to say you're failing grade 8. It's the reverse. I'm trying to say, know that you have tackled all this kind of stuff since grade 8. You have. The reason why you don't like it is because you've got log 2 there instead of 7. You know? If I had said to you this problem here, going on to slide 7 to show you what I mean. If I'd said to you, solve for x, who here would say, oh, well, Richard, what do you expect? We can't do that. Get stuff, Richard. Who would say that? I mean, who would say it and mean it? But you wouldn't though, would you? All I've done here is that the 7 is log 2 and the 5 is, sorry, the 3, oh yeah, it's 5 in this case. 5 is log 5. Look, the numbers have got more complicated looking, but the process is grade 8, grade 9 level. Just those 3 letters to make it. Which is why I said that, again, I apologize if that made me sound like as if I was saying that you're a failure if you can't do it. That wasn't my point. My point is, don't worry, you've done these processes from year 8. Don't get bamboozled by the fact we've got logs floating about all over the place. The only problem with the logs is it means that you can't go, well, 3 5s are 15. You have to leave it as 3 log 2 for a while. That's all. Okay? It's just a number at the end, though. So it's complicated but not complex. Just call me Richard. I much prefer it. Yes, Archie. Yep. Yes, you go to the math study and they can fix it in about 5 seconds. I've said this to you before. Yeah.
Overnight tonight and get it tomorrow if I do.
Do what?
My land leave it overnight.
Leave what? Yeah.
And then just randomly gone to Preston test mode. I don't know why. It's like actually flashes. So
okay, I'm going to finish this problem up now while you're continuing work. Can you see that the rest of this is just plug it all into your calculator and see what works? Okay, but I can see when I reached for my calculator and started to do it, so I put the answer down, you just launched into chat mode. So I'm going to stop, you get on with your work, and we'll move on in about 3 minutes. So see if you can get one more problem out in 3 minutes. In between example 1 and example 2, we did have sort of example 2-ish there. So example 2 there. So this is example 2-ish. Exercise 4Q simply asks you to give your answers in a particular form. So no calculator required. You really should be paying attention to what's happening right now. Okay, so you have to express your answer in the form natural log A over natural log B. So you can't just choose any which way you want to. It needs to be expressed in this particular format. So everything you do needs to be getting it closer and closer to this goal. You can't just be as random as you would like to be. You need to consider carefully where you're headed. So here's the actual equation, which is 4 to the power of x minus 3 times 2 to the power of x is equal to 0. Now, there's a bunch of ways you could start solving this, but this is the way we're going to do it. I'm going to add 3 times 2 to the power of x to both sides. So I've got 4 to the power of x is equal to 3 times 2 to the power of x, like so. And we've got a start. Now, what I'm going to do is I'm going to take not just any logarithm, but the natural log of both sides. I take the natural log because I know that's where I'm headed. I'm using square brackets just because I'm using round brackets on the inside. That's all. They don't mean anything special. Right so far? I'm going to run out of room if I don't maximize that screen.
So how come calculators on your iPad are not coming up on the screen?
Because I'm not broadcasting my iPad page. I'm broadcasting the information in the app. Okay, I'm now going to use my my old friend, the multiplication or product rule for logarithms, to split it up a little bit. So I've got ln 4 to the power of x, which is equal to ln 3 plus ln 2 to the power of x. What I know, ladies and gentlemen, is I know I need to get to those powers. What I also know, I'm trying to give you an insight into the thought process. What I also know is that this isn't a number raised to the power of x, right? It's 3 times a number raised to the power of x. So I can't straight away take that x and bring it down. Do you see what I mean? Log rules are almost everything in maths is the same. If it doesn't fit a pattern exactly, then you can't use it. If you do, you're just applying mathemagic. Over here in blue, I'll show you what I mean. What I'm saying is that the rule exactly is log base a b to the x is equal to x log base a b. That power can go down. That's the exact rule. The rule is not log base a yb to the x equals x log base a yb or anything like that. That's not true. Okay, if it doesn't fit the pattern exactly, then you have to do work until it does fit the pattern exactly. So I can't just bring down the x straight away because this is a compound term. It's made up of a bunch of things. Okay, but now I've got it split. I can now say that's equal to x natural log 4, and we've got ln 3 plus x ln 2. So I can now bring down the x because it was in exactly the right format. Jeremy, was that a question? Someone else answer. Zoe, you answer Jeremy. Yeah, great. Thanks, Zoe. So just for the video's sake, Jeremy said, why choose natural log instead of log base 10 or something else? And the answer is because the question wanted us to write it in natural log form. Yeah, 4Q. Did I not write that down? Yeah, I did. Exercise 4Q, 3B. I'll just move on. I'll answer that question in a minute because I'm not too sure what the story is there. So the next thing I'm going to do is I'm going to subtract XLN2 from both sides. I'm not writing this down, so I hope that you're listening. So I subtract XLN2 from both sides because I'm isolating X to one side of the equation. So I've got XLN4 minus XLN2 over equals LN3. Notice my use of brackets is just going all over the shop here. Okay, doesn't matter whether you use brackets or not, unless you've got a really complex term like this where then you really have to put brackets in. Okay, I'm nearly there. I'm now going to isolate the X even further. So I've got XLN4 minus LN2 equals LN3. And now I can divide both sides by LN4 minus LN2. So I get LN3 all over LN4 minus LN2. Now, the lazy amongst you might go, and my job is done. I've got a fraction, I've got natural logs, I am cooking with gas. But the answer is not quite right yet. And the reason why is because it's not one log divided by another log. Okay? And I mean it. You need to be precise with your thinking. I shouldn't say lazy because no one here is lazy. Sloppy. You can't be sloppy with your thinking and say near enough is good enough. Mathematics is about precision. If it says ln A over ln B, then that's exactly what you need to deliver. ln over ln. I need to go to the next slide to finish this off because I'm not going to fit it in very easily. I'll repeat that last line on the next page so you can see it. So it was x equals, I'm sorry, what was it? X equals ln. Thank you. Stereo. Okay. So that's what we ended the last page with. Now, good news is the top is looking good. ln3 is exactly what we want. ln something is what we want. It's the bottom that's we're having a bit of trouble with. But what we do know is that when I have two logarithms that are subtracted from each other, the quotient rule takes over. So that gives me ln3 over ln4 divided by 2. And now we're done. Archie, I'm not too sure whether either A, you were away, or B, you were asleep. Both are possible, but we did it a couple of lessons back now, and it's all on Google Classroom. Archie, did you notice that I use the product rule here? Were you satisfied with that as a step? We did it in the same lesson. Fell asleep. It's all good. Happens to the best of it. Best of us. Okay, 4Q, you've got 5 minutes to complete 4Q. Anything you can do from 4Q? When the squabbling starts, Richard goes back to teaching. So, example 3. Now, I was trying to find the one from exercise 4R. I was trying to find one from exercise 4R that would sort of spell out exactly what we need to do, but I couldn't find one that I was confident on. So I want to have a look at example 27, example 28. Yeah, that's perfect. So example 28 asks us to solve the following equation. ln of 12 minus x equals ln x plus ln x minus 5. Notice that I absolutely have to use brackets when the argument, that's the value I'm inputting into the function, is more than just a single number. So although I can get away with not using it here, I absolutely have to use it here and here. Otherwise, it might be ln x minus the value 5. You paying attention, Zoe? Great. So first things first, we are going to use a very simple principle, which is basically if I can express both sides of the equation as a single log, then I can equate the arguments, the inside bits. I'll show you what I mean. The left-hand side, so this is the solution. The left-hand side, I just keep it as it is because it's already a single log. On the right-hand side, I've got ln x plus ln x minus 5. I've done nothing yet. All right. Okay, this is the solution. Okay, so the right-hand side is 2 logs that have been added together, same base, because they're both natural logs, so I can combine them using the product rule. And I'm going to use square brackets just so that it doesn't get too messy there with my brackets. So on the left-hand side, I have ln 12 minus x. On the right-hand side, I have ln x times x minus 5 using the product rule for logarithms. Now that I've got a log on both sides and I've got a log on the other side, I can now equate the arguments. This is the equivalent of raising both sides to the e to the power of. Basically, the ln's cancel out. So I've got 12 minus x is equal to x outside of x minus 5. Okay, this is a problem you have been solving probably since year 10, and that is it's an equation with x on both sides. It's going to be a quadratic. Let's go for it. So on the left-hand side, I've got 12 minus x. I expand the right-hand side to get x squared minus 5x. I then move all the x's onto one side. We do that by removing them from the side where they appear least, I guess, is the safest thing to do. And so I'm left with 12 is equal to x squared minus 4x. And because I've got a quadratic, I know that I'll need to use quadratic tools in order to solve this. So I'm going to have to subtract 12 as well. So switching sides, I've got x squared minus 4x minus 12 is equal to 0. Okay, I just subtracted 12 from both sides and then flip the sides. Okay, this is a quadratic which can be factorized into x minus 6 times x minus x plus 2. Yep, x plus 2 is equal to 0 because 6 2s are 12 and 6 minus 6 plus 2 is negative 4. And therefore, by the null factor law, x is equal to 6 or x is equal to negative 2. We haven't quite finished, but can you see what I've done so far? So simple uses of the log rules. What makes this complicated is that you then need to draw from another tool, part of your toolbox, the bit which has quadratics in it. But we haven't quite finished the story yet. Does anyone have any questions?
Yeah, that's the sort of stuff.
Possibly, I don't know. I can't remember. Okay, this is the thing though. But if x equals negative 2, then x minus 5 equals negative 7, and ln of negative 7 does not exist. Therefore, x equals 6 is the only solution. You don't have to be so wordy when you're doing it yourself. I'm putting it in lots of words so you can, when you're reading back, you can see it. But effectively, what you need to do once you've got answers, solutions for x, is not simply to say, oh, x equals negative 2 does not work. So you need to simply go test each of the values of x in the logarithm functions that you've got. And if any of them return a negative number, then you can discard them as a solution. Okay? Because remember, logs can't have negative arguments. So tomorrow's work, whether I'm here or not, will be working through exercise 4R and 4S, and then going back into P and Q and trying those. Any questions?
I have a question.
I'll just stop it and then I'll take questions, but you are welcome to leave, guys. I'm sorry I was so rushed today.